And again, as I just mentioned, HPC is the future. HPC is the high performance computing. So you have yesterday's supercomputer was, you needed a huge lab for it, big building to hold the computer. But today, as things are getting better, you have the same supercomputing capability on your phone, right? I mean, your phone can pretty much do everything yesterday's supercomputer would do. So going down the line, we'll end up with devices that are extremely capable, that are extremely fast, very precise. You can play insane games just on your phone. So that's where things are heading today. As we have the increase in IoT, as we have got higher interest in IoT, so you need things that consume lesser power. Say, for example, I put in a sensor to detect if my door is closed or not. I mean, I cannot expect to keep changing the battery every 2 days, right? So my idea would be I put in the sensor and forget about it. So for this, I need ICs that consume extremely less power. So maybe just a couple of microamps, and I put in a battery and I just forget about it. It has to keep running forever. So these are the applications that target low power consumption, and yet they should give you high performance. So I cannot have a low power, but oh, it doesn't work well. It does very basic things. No, I need a low power consuming device that is capable of doing amazing work. So MSP430 is one such microcontroller. Extremely low power, you can run it on, say, a couple of microamps. Microamps of current is, I had seen an interesting poster where somebody had run an MSP430 using an apple, the fruit. It seems it's capable of producing current in the microamps range, and that is sufficient to run an MSP430. So that's how things are moving today. And warehouse scale computer. So you might have obviously used Facebook, Instagram, YouTube, Google, etc., right? I mean, just think about YouTube. Every day there are millions of people uploading videos. Each video is high quality 4K video running into a couple of minutes or hours. Where do you think they store all this? And when I search for a particular video, I get the video instantaneously, right? I don't have to wait for, like, say, half an hour. Half an hour later, I'm going to get the video. No, that doesn't happen. So these are huge computers, almost similar to a supercomputer, and they've got massive data storage capability. So that's where they keep all these databases. That's a way to scale computer. So a lot of people are also working on these topics now. Going down the line, if you're interested in trying to understand what are the research problems that are present in this domain, if you want to, get yourself involved in something where you can innovate, or where you can solve some problems, I have listed 3 of the most basic research problems that we are facing today. Nonetheless, I mean, definitely there are a lot of other research problems which you can definitely look into, but these 3 are something that I felt are extremely basic and extremely important from the programmer point of view. The first one. So have you ever wondered why the number of cores keep on increasing? I told you that Pentium was the first one to have dual core, right? And then we had octa core, we had 16 cores, and we had 32. But it somehow saturated. I mean, it didn't skyrocket. I don't have a phone that has got 1,000 cores in it. Why do you think that doesn't happen? So I have 2 sub questions here. So the first question would be, why do you need more cores? I mean, why can't I just be done with single core? Why do I need 8? Why do I need octa, tera, etc., etc.? And why doesn't the number of cores just increase? Why don't I have 10,000 core CPU? So these are 2 questions on which I just want you to think for probably the next 15 seconds, after which I'm going to give you the answer. Okay, so the first one, why does the number of cores keep on increasing? Simply put, because I need more capability, I need more processing power. I know that a single core can now give me only so much performance. I've now pushed it to the limit. I want more performance. So what do I do? Simple, put in more cores. So that's the reason why cores kept on increasing. And the second question I asked was, why can't I have CPU with, say, 1,000 cores? If increasing the cores is the solution, simple, right? I'll just have a CPU with 1,000 of 2,000 cores, and now it's like running amazingly well. So the reason for this not happening is because of something known as Amdahl's law. So this is the most basic law of computer architecture. So I can probably say, what is Newton's law for physics? Amdahl's law is for computer architecture. So Amdahl's law says that It basically talks about how much speed up I can achieve by adding more processors. And unfortunately, it seems according to this law, if I end up adding too many processors, too many cores together, it will actually make the system very bad. So there are situations wherein people have added, say, 32 cores, 64 cores, and it really messed up in such a bad way that they had to go back to their 8-core or 2-core design. So that's because of the Amdahl's law. And one more thing that you might have noticed is when you buy a new computer, you see that okay, Intel i7, it's on a 14 nanometer technology. Snapdragon 850, 848, it's on a 10 nanometer technology. Exynos by Samsung is on a 7 nanometer technology. What exactly is this 7 nanometers, 10 nanometers, 14 nanometers? What is this thing? I think if you're from the electrical or electronic background, you might have already known this. So this is the size of the transistor that makes up the IC. I think all of you would already know by now that every IC has got is made up of transistors, right? So every chip that I see around me is definitely made up of just one thing, and that is transistors. And if I want to make my IC more compact and more powerful, what do? I increase the number of transistors. But physics has got its limits. Moore's law was a law which said that every 18 months, the number of transistors on a chip doubles. So he said this somewhere in the 1960s. So Gordon Moore was the founder of Intel. So he's a very famous guy. And what he said way back in 1960 was the number of transistors on a chip doubles every 18 months. So that actually kept true for a very long time, for almost 40 years that happened. So every year, the number of transistors on a chip doubled to an extent where in today's processor, you'll find literally billions of transistors. But now we have reached a limit where physics doesn't allow that anymore. So I cannot have a transistor that's smaller than 5 nanometers because each atom itself is 1 nanometer long. How smaller can I go? I cannot have something much smaller than an atom, right? So this is a very big challenge that has faced the industry now. So the size of transistor cannot increase now. How do I pack in more transistors in my chip? I mean, I don't want to have a phone that's 1 feet by 1 feet just because I want to have a huge processor, right? I want to still have a very small phone, but that's very capable. So how do I do it? I cannot fit in any more transistors now. So that's one big challenge that has faced us. And people have come up with a lot of innovative designs, like they've come with FinFETs and NEMT CMOS transistors. So many different designs have been proposed to kind of tackle this, but nobody can definitely have a smaller transistor. So we are kind of saturated. Physics doesn't simply allow us to go any smaller. So we just have to find ways around this now. So that's huge research that's happening. And one more interesting question that I have you ever wondered why my processor doesn't go beyond 5 gigahertz? I mean, I still remember when I first bought my computer. I mean, when my parents bought the computer, so that was a Pentium computer, and I think it ran at about 2 point something gigahertz. And I recently bought a laptop that ran at 4 point something gigahertz. So, I mean, in the span of 15, 20 years, it's just increased by a few gigahertz, the clock speed. Ever wondered why that happens? Why can't I have a processor that runs at 10 gigahertz? I mean, the faster it runs, the faster it can compute, right? So I'll end up having a super fast computer. I mean, I can just open my YouTube and start editing 4K videos without any issue in such a case. But have you ever wondered why I cannot have a 10 gigahertz computer and why it is kind of stalled at 4.5 gigahertz? So the answer to this is in a law called Dennard's law. I'll tell it in a very simple way. The reason is power. So today's processors, the biggest issue they face is the power consumption. So in fact, you can look at some very interesting researchers that say that the power consumed by a processor per unit area is equivalent to a rocket. So you've seen a rocket engine, right? You've seen so much heat it produces. It seems the per area power consumption is both the same. A processor consumes so much power. So that's the reason why I cannot clock it at faster rates. So if I clock it at say 5 gigahertz or 10 gigahertz, I'll end up with burning the processor. So that's a big challenge that we face today. So these are one of the few open research challenges that you can have a look at. You'll be able to see a lot of other innovative designs that people have come. People have made changes in the architecture. They've come up with innovative compilers. They've come up with different programming designs to make sure that these challenges can be overcome. But simply put, I mean, these are the realities that is posed by physics. I cannot really bring my transistor size to be any smaller. Physics doesn't allow it. And Amdahl's law says that I cannot blindly put in number of cores. I just can't keep increasing that. That's also not possible. And I cannot clock it faster because, I mean, I want a laptop. I don't want a fridge, right? I mean, I don't want a fridge attached to my laptop just because I want to cool my processor. So these are the different trade-offs that we see in the industry. And if you are really interested, I think these are great places to explore. So we've already come to one of the last few slides. So what are the different skills that a person must have to, survive in the industry, thrive in the industry, and have fun, most importantly, in the industry is you have to understand the microprocessor and controller architecture. So you have to understand, okay, given a processor, this is what it will contain. Any processor for that matter will have so and so, so and so, and so and so. Just like a car, if I see a car, I know that okay, it's got 6 gears, I've got 1 reverse, I have a brake, I have a clutch, I have an accelerator, I have a steering wheel. It can be an imported car, it can be a small car, it can be a big car. In fact, a bus will also have a similar architecture, right? But I need slightly different experience for that. So the analogy is very similar here also. I mean, most of the microprocessors, most of the controllers will have the same set of architecture. But if I go into, say, GPU, if I go into FPGA, it's like going into a bus. It will again have the same set of architecture, but something additional. So in that case, you'll have to probably learn that quickly and start working on it. So I have listed a couple of topics here. So that would include memory management. So memory hierarchy and caches. This is something that's really interesting and very, very easy to learn as well. As in, you might have known by now, right? RAM is something really fast. If I've got some data in my RAM, I can easily access it very quickly. But if I've got the same data on my hard disk, so the power banks that you have, the memory banks that you have by Toshiba, the 1 GB, 1 TB, 2 TB memory banks, they're very slow. I mean, you want to put a movie into it, it probably takes 10 minutes, right? But if I want to copy a movie from one folder to another, it happens in, say, less than a couple of seconds. So that's because RAM is faster than your secondary storage. So that is defined by what is known as memory hierarchy. So that is something that you have to understand. And the instruction set architecture, as I previously said, it's a contract between the programmer, the software engineer, and the hardware. So the person should know that, okay, this is what the hardware is capable of. This is what the hardware gives me. And based on that, you start coding it. And you have some other concepts like what are interrupts, what are polling, what are timers, what are ADCs, etc., that you come across in your microcontroller. Say, for example, you are working on a project and the customer says that, okay, give me a project wherein I want to run an operating system in my TV. So I want to have an Android TV. So can you design that? So that's the high level requirement that's given to you. So you now have to break it down that, okay, if I have to have an Android running on my TV, I'll probably need a very good chip that will support different interrupts, that will support so and so protocols, that have so much memory, that has so much compatibility, etc., etc. So that's something that you have to understand. And say, for example, you want to connect a mouse to the TV. So how will you do it? So you'll need some communication protocols like SPI, UART, I2C, CAN, FlexRay. So these are different protocols through which I can connect external devices. So I want to say connect the DTH to my TV. So how will that happen? That'll probably happen over SPI or I2C. And then there are architecture level units like a branch predictor. So, when I encounter a for loop, so how does that for loop executed? Is there any way I can make it much faster? Do I really have to run the iteration 1,000 times, or can I do it much faster? Such things are implemented in a branch predictor. And when you look at a microprocessor, it might say that, okay, this supports multi-threading. This supports instruction level parallelism. It has got 8 cores in it, and each core supports 2 threads. So, and how do you exploit that? How do you make sure that, okay, I'm now running 2 threads on the same core simultaneously so that my job happens much quicker? How do you understand that? How do you exploit it? So these are the things that you should understand to do well in the industry. And of course, programming. So you have to be good in C programming, but you don't really require to be an expert. It doesn't require high level C programming concepts. You have to be good in pointers, arrays, structures, linked list, and such thing. And last but not the least, you will have to know the basic electronic concepts like what is voltage, what is current, what is a potential drop, and how much is the reverse bias voltage that this particular junction requires, and what's a transistor. Knowing these things really makes you appreciate that, okay, this is what I did now and this is what happened. So I think without basic electronic concepts in your mind, it's like shooting the arrow in the dark. You know that, okay, it might hit, it might not hit, and tomorrow you have to debug some issue and you're not sure that why is this not working. Is it because of, I've added more voltage, or it's the current is not enough. So if you have to debug in that direction, then the concepts of electronics is definitely required. The last slide. So what is a career path? So a skilled engineer in this domain, where will he end up? So these are some really interesting names that you want to be associated with, right? Intel, Samsung, ARM, Apple, Nvidia. So these are the places where people work on semiconductors. So some of these guys directly design processors. Samsung does it, Qualcomm does it, Intel does it, AMD does it. ARM gives the license, as in it gives them the design. So it says, okay, this is a great processor, this is the design. You can use this design and come up with your own flavors. That's what ARM does. And some of the other guys, maybe smaller companies like maybe I don't know the names, but smaller companies might use these processors and come up with their own designs. I probably an IoT company that says that, okay, you've got a smart home system, and all of them use devices made by these companies. So the industry is huge. I mean, it's just not these names that I put on the screen, but literally thousands of companies across the world are hiring, are currently working with these engineers. So the person who's skilled in this domain ends up being a software engineer, then he becomes a staff engineer, then they become architects, principal engineers, and so on. So Germany, South Korea, Japan, India, of course, and USA. So these are some countries where great work is happening in this domain. So in case you want to work in some of these places, then this domain will really come handy. So I think I've come to the end of my slide.